What's happening, guys, and welcome back to our channel. Experiments fuel science in the same way as gasoline fuels a car. It's a fundamental scientific principle that if you have a hypothesis about how the world works, you must test it with an experiment like the scientists mentioned below did. Get your popcorn ready, because we're going to tell you about the 5 amazing experiments explained. Number 5. The Pendulum of Foucault. When scientists placed a pendulum over the South Pole last year and watched it swing, they were reenacting the famous experiment from 1851 in Paris. The French physicist Jean-Bernard Léon Foucault suspended a 62-pound iron ball from the Pantheon's dome with a 220-foot steel cable and set it in motion, swaying back and forth. He connected a stylus to the ball and set a ring of moist sand on the floor below to track its movement. The crowd gasped in amazement as the pendulum appeared to revolve strangely, each swing leaving a slightly different imprint. The Pantheon's floor was gently moving, and Foucault had demonstrated more conclusively than ever before that the planet rotates on its axis. The pendulum's route would complete a full clockwise revolution every 30 hours at the latitude of Paris. It would rotate counterclockwise in the southern hemisphere, and it would not circle at all at the equator. The period of rotation at the South Pole is 24 hours, as contemporary scientists have proven. Number 4. Discovery of the structure of DNA. The structure of DNA, the molecule that carries our genetic material with 2 strands weaving in and out of another in a pattern known as a double helix, was discovered by Francis Crick and James Watson in 1962, and they shared the Nobel Prize in Physiology or Medicine with Maurice Wilkins, who had done some of the X-ray diffraction studies that Crick and Watson had done. X-ray diffraction is similar to shadow puppetry in that you use an X-ray beam to cast accurate shadows of a material's atomic structure onto a photographic plate rather than a flashlight to cast shadows of your hands and draw animal silhouettes on the wall. Franklin had obtained a very significant X-ray diffraction photograph which showed a great deal about the structure of DNA. Even though scientists have verified the critical relevance of her work, she has never achieved the same level of notoriety as Crick, Watson, and Wilkins. In fact, most non-scientists are unfamiliar with her name. Number 3. Discovery of a single electron's charge. The precise value of a single electron's charge was discovered in this experiment, which took place in 1909. Robert Millikan had done well for himself by most standards. He was born in a tiny Illinois village in 1868 and went on to Oberlin College and Columbia University for his education. In Germany, he studied physics with European superstars. He later became a professor of physics at the University of Chicago, where he also wrote some popular textbooks. His co-workers, on the other hand, were doing considerably more. The world was introduced to quantum physics, special relativity, and the electron, the first proof that atoms had divisible components in just over a decade at the beginning of the 20th century. Millikan was approaching 40 years in 1908 and had yet to make a big discovery. The electron, on the other hand, presented an opportunity. Researchers debated whether the particle constituted a universally consistent basic unit of electric charge. It was a pivotal decision in the development of particle physics. Millikan took a chance because he had nothing to lose. He began experimenting with cloud chambers, containers of dense water vapor, at his lab at the University of Chicago, and changing the strength of an electric field within them. Before falling owing to gravity, clouds of water droplets formed around charged atoms and molecules. He could slow or even stop a single droplet's descent by changing the intensity of the electric field, thus counteracting gravity using electricity. Number 2. How does blood circulation take place? The discovery of blood circulation was the outcome of an experiment, and the theory was published in 1628. In the 2nd century, a Greek physician-philosopher presented a model of blood flow that, despite its flaws, endured for over 1,500 years. The liver continually produces new blood from the food we consume. Blood travels throughout the body in two streams, one of which is infused with vital spirits from the air through the lungs, and the blood that tissues absorb never returns to the heart. It took a series of often horrific tests to debunk all this orthodoxy. William Harvey had begun by exsanguinating or draining the blood from test animals such as lambs and pigs to attack the Galenic paradigm, literally in some cases. Harvey recognized that if Galen was correct, the heart would have to pump an inconceivable amount of blood through it every hour, far beyond the size of the animals. Harvey demonstrated this point by slicing open live animals in front of the audience, displaying their limited blood supply. He also finger-pinched a major vein in a snake's exposed heart to stop blood flow. The heart shrank and paled, and when punctured, it flowed forth just a small amount of blood. Choking off the major leaving artery, on the other hand, caused the heart to enlarge. He identified the heart's contractions by studying the sluggish heartbeats of reptiles and animals near death and inferred that it circulated blood through the body in a circuit. Harvey's inference was not simple, according to Andrew Gregory, a professor of history and philosophy of science at University College London. If you look at a heart beating normally in its normal surroundings, it's very difficult to work out what's happening, he adds. Experiments with willing participants in which blood flow in and out of limbs was briefly blocked backed up Harvey's innovative theory of blood circulation. In 1628, he wrote De Motu Cortis, the motion of the heart, which contained the entire idea. His evidence-based approach revolutionized medical research, earning him the title of Father of Modern Medicine and Physiology today. Number 1. Measurement of Earth's circumference. The first known measurement of the Earth's circumference was made in this experiment. It was performed at the end of the 3rd century BC. What is the size of our universe? An astonishingly precise value determined by Eratosthenes has resonated down the years among the various replies from ancient societies. Eratosthenes was born in 276 BC in Cyrene, a Greek town on the coast of modern-day Libya. He was a voracious learner, which drew both fans and detractors. University of Puget Sound physics professor James Evans explains the classical style burn. Eratosthenes moved so often from one field to another that his contemporaries thought of him as only second best in each of them. The scholar's mental prowess won him a job as chief librarian at Alexandria's famed library. It was there that he carried out his well-known experiment. On the day of the Northern Hemisphere summer solstice, he had heard of a well at Syene, a Nile River city to the south, which is modern-day Aswan, where the noon sun shined directly down, casting no shadows. Eratosthenes was intrigued, so he measured the shadow cast by a vertical stick in Alexandria on the same day at the same hour. The angle of the sun's illumination there was 7.2 degrees, or 1/50th of a circle's 360 degrees according to him. Knowing that the earth was spherical, as did many educated Greeks, Eratosthenes reasoned that if he knew the distance between the two towns, he could multiply that figure by 50 and calculate the curvature of the earth and therefore its completed circumference. With this data, Eratosthenes calculated the circumference of the earth to be 250,000 stadia, a Hellenistic measure of length equaling about 600 feet. Eratosthenes' motivation for getting the Earth's size right was his interest in geography, which he named after himself. Modernity was conferred upon him yet another moniker, the father of geography. Not bad for a person who was once considered second-rate, right? Do you know of any other historic experiment that you think deserves a spot in this video? If so, do let us know in the comments down below. And as always, I'll catch you guys later in another video. Bye now!